High above the familiar clouds and the very air we breathe, where the sky fades into the blackness of space, lies the ionosphere, a vast, often unseen yet incredibly important shield protecting our world from the harsh environment of space. It's not quite the vacuum of space, nor is it the dense, comforting lower atmosphere that sustains life as we know it. Instead, it's a dynamic and ever-changing region, a critical boundary where Earth intimately meets the sun's energy. Starting approximately 50 miles above the Earth's surface, the ionosphere stretches hundreds of miles outwards, gradually fading into the emptiness of space. It's a truly vast region. This creates a layer of electrically charged particles that is absolutely crucial, not only to the natural world, but also to our modern technology. The sun's intense ultraviolet and X-ray radiation constantly bombards our upper atmosphere, forcefully knocking electrons loose from their atoms, a fundamental process known as ionization. This ionization process results in the creation of a sea of free electrons and positively charged ions, ultimately forming what we call plasma, the very essence and defining characteristic of the ionosphere. The ionosphere is far from static. It's a dynamic and restless environment. It constantly swells and contracts, undergoing significant changes in response to the daily cycle of the sun and the shifting seasons. During the daytime, the constant influx of solar energy thickens and energizes the ionosphere, increasing its density. While at night, as the sun's influence wanes, it gradually thins as electrons slowly recombine with ions, reducing its density. This vital layer acts as Earth's natural and first line of defense, a kind of sunscreen, diligently absorbing much of the harmful solar radiation, and ultimately making life on our planet possible. But the ionosphere's role extends far beyond simple protection. It actively interacts with our technology in complex and often unpredictable ways, influencing the performance of critical systems. Its ever-changing nature can either disrupt or enhance the radio signals that we rely on for communication, navigation, and countless other applications. Therefore, gaining a deeper understanding of this dynamic region is absolutely essential for successfully navigating our increasingly technological future. The ionosphere is truly a living, breathing, and incredibly active part of our planet's overall environment. It's a critical region of space weather that subtly yet significantly shapes many aspects of our daily lives, often operating behind the scenes without us even realizing its profound influence. And as our dependence on space-based technology continues to grow, the importance of fully understanding the ionosphere will only continue to increase. It's far more than just a scientific curiosity confined to research labs. It's an absolutely vital and integral part of our world. In essence, the story of the ionosphere is also the story of our planet's intricate and ongoing connection to the sun, and it's a fascinating story that we're only just beginning to fully piece together and understand in all its complexity. The ionosphere, a dynamic layer of our atmosphere, is both a bridge and a sometimes unpredictable barrier for our communication systems. It plays a crucial role in how radio waves propagate around the globe. For decades, radio operators ingeniously bounced signals off it, a technique known as sky wave propagation. They were effectively using the sky itself as a global network, long before the internet even existed. This skywave propagation allowed radio signals to travel thousands of miles, bending around the curvature of the Earth. It was connecting continents and enabling global communication before satellites even existed. This was a revolutionary technology of its time. But the ionosphere is turbulent, a constantly shifting sea of charged particles. Space weather events like geomagnetic storms and solar flares can severely disrupt or even completely block these signals, leading to significant communication challenges. This can result in radio blackouts, leaving regions isolated and emergency services hampered. Solar storms in particular can supercharge the plasma within the ionosphere, dramatically altering its properties. This can lead to the absorption of radio waves, effectively silencing communications for extended periods of time. GPS satellites, which orbit high above the ionosphere, must transmit their signals through this dynamic layer in order to reach receivers on Earth. The plasma within the ionosphere bends and delays these signals as they pass through. This can sometimes throw off GPS accuracy by several feet, introducing errors in positioning. For critical applications like aviation and precision farming, such seemingly small errors can have significant and even critical consequences for safety and efficiency. The ionosphere's unpredictable changes can degrade signal quality, introduce unwanted radio noise, or in extreme cases cause complete communications outages and system failures. This complex interplay of factors is what we call space weather, a constant and evolving challenge for our increasingly technology-dependent world. Therefore, understanding and accurately forecasting the ionosphere's ever-changing moods is absolutely essential for maintaining reliable communications and ensuring the accuracy of our navigation systems. Our modern world, with its reliance on satellite communications and GPS, critically depends on it. Studying the ionosphere isn't just an academic scientific pursuit, it's an absolute necessity for protecting our technology and infrastructure. We must continue to learn to predict and adapt to its dynamic and ever-changing nature, ensuring the resilience of our technological systems in the face of space weather. To truly understand the ionosphere, a region of our atmosphere teeming with charged particles, we need to venture beyond the reach of ground-based instruments. It's a complex and dynamic environment, constantly shaped by solar activity and interactions with Earth's magnetic field. To get a complete picture, we have to go there. We need to send probes directly into this atmospheric layer to gather detailed in-situ measurements. That's where NASA's SEED mission comes in. Sporadic-E experiment on density, a focused effort to unravel the secrets of these fleeting atmospheric phenomena. It uses sounding rockets for short targeted flights, providing a cost-effective way to access the ionosphere. Unlike satellites, which offer long-term monitoring, these rockets launch, collect data in minutes, and return to Earth, allowing for rapid deployment and focused investigations. SEED's primary goal is to fly directly through mysterious dense plasma clouds called Sporadic-E, which can disrupt radio communications. Ground-based instruments like radar can detect these clouds from afar, but only a rocket equipped with specialized sensors can measure their properties up close and in detail. Scientists meticulously monitor space weather, carefully watching and waiting for a sporadic E cloud to form in the right location, then launch the rocket at just the right moment, ensuring it intersects the cloud. As it ascends, the rocket releases a visible vapor trail, letting scientists on the ground track upper-level winds and turbulence, providing valuable contextual information. Onboard instruments measure the plasma's density, temperature, and composition as the rocket passes through the sporadic E cloud. This coordinated approach gives a multi-layered view of the ionosphere, combining ground observations, wind tracking data, and direct measurements from the rocket-borne instruments. The resulting data is invaluable for testing existing theories and refining complex models of the ionosphere's behavior. SEED captures fleeting events and gathers data that ground-based tools simply can't access. It's targeted science in action, providing critical insights into a dynamic region of our atmosphere. Ultimately, SEED is key to solving the mystery of these disruptive plasma clouds and improving our understanding of the ionosphere. What are these sporadic E clouds? Their name says it all. They're unpredictable, appearing and vanishing without warning. Forming in the E region of the ionosphere about 60 to 75 miles up, they're invisible but incredibly dense patches of metallic plasma. These clouds form when high-altitude winds compress heavy metallic ions, like iron and magnesium from meteoroids, into thin layers. Sporadic E clouds can be over 100 times denser than the surrounding plasma, making them powerful reflectors of radio signals. For amateur radio operators, this means surprise, long-distance contacts, E-skip. But for commercial systems, these clouds can cause major interference, bouncing signals far from their intended path. This disrupts radio, TV, and even aviation communications. Understanding how and why sporadic E forms is crucial for predicting and preventing signal disruptions. These clouds are a puzzle with real-world consequences. Solving it keeps our communication systems reliable. While SEED gives us close-ups, NASA's GOLD mission provides the big picture. GOLD is an instrument on a commercial satellite in geostationary orbit, staring continuously at the Americas. It observes the ionosphere by detecting air glow, faint ultraviolet light emitted by excited atoms and molecules. By analyzing this light, GOLD maps the temperature, composition, and density of the ionosphere across a hemisphere. Before GOLD, our view was fragmented. Now we have daily, global-scale measurements. GOLD tracks how the ionosphere responds to solar storms and even weather patterns from below, like hurricanes. It reveals how the region heats and cools, expands and contracts. GOLD's constant watch helps us see changes as they unfold in real time. It's our sentinel, providing the data needed to understand and forecast space weather. With GOLD, we finally have a weather map for the edge of space. Science often surprises us, and GOLD did just that. While monitoring the equator after sunset, GOLD spotted vast, X-shaped plasma structures connecting dense bands, features our models never predicted. These X-shapes stretch for hundreds of miles and are linked to turbulent plasma bubbles that disrupt satellite communications and GPS. The discovery revealed new dynamics in how plasma moves along Earth's magnetic field. Gould's global view was key to spotting this pattern. Understanding these X-shapes helps scientists improve models and predict disruptive plasma bubbles. Better models mean better space weather forecasts. This discovery is a leap forward in protecting our technology. Sometimes looking in a new way changes everything. Studying the ionosphere isn't just academic, it impacts your daily life. GPS, smartphones, and navigation systems all rely on signals passing through the ionosphere. By understanding plasma clouds and disruptions, we can correct GPS errors and improve accuracy. Data from SEED and Gould feeds into models that help refine GPS algorithms and forecast outages. This research also protects air travel, satellite TV, and even internet services from unexpected disruptions. Space weather can damage satellites, but better understanding helps us design more resilient systems. Forecasts allow operators to safeguard satellites during storms. Studying the ionosphere keeps our technology running smoothly. It's about protecting the infrastructure we depend on every day. Space weather is as real as rain or wind, just less visible. The ionosphere is where space weather directly affects us, disrupting signals and technology. Missions like Gould and SEED are our space weather stations, feeding data into models that forecast disruptions. Discoveries like Gould's X-shapes help us improve these forecasts. The goal: reliable warnings for airlines, power grids, and more. Space weather doesn't respect borders, it's a global challenge. By sharing data worldwide, we build a complete picture and protect our way of life. We're learning to read the signs of space, turning knowledge into action. Our quest to understand the ionosphere is part of humanity's drive to explore. Missions like SEED and Gould are our modern ships, charting the invisible ocean above. Each discovery, whether a plasma cloud or an X-shape, adds to our map of the cosmos. This research isn't just curiosity, it's vital for protecting our technology and way of life. As we rely more on satellites, understanding their environment becomes critical. We keep looking up, launching rockets and building new instruments because the universe is full of mysteries. The challenges we face demand new knowledge and solutions. By studying the ionosphere, we protect our future and continue our journey into the cosmos. The ionosphere is just one frontier, but it teaches us about our home and our place in the universe. Our exploration enriches us all, and it's only just beginning.